So, however, very close to the demonstration of this lemma, so I'd like to comment it. And in this particular example, the power of canonical transformation is present, is evident. So let us understand what is written here. So we can consider just the Hamiltonians, just the Hamiltonians which are coefficients of this expression, and consider the conjugated variables to these Hamiltonians. It means the times with respect to these Hamiltonian flows. And okay, what is this equation here? It is an equation of the second order, differential equation on S of the second order. And if we solve this equation, so if for each choice of values of Hamiltonians, we could find such a function S of one variable Z, such that it solves this equation, then it gives a good generating function of our canonical transform. So we have only to prove that ds over dy I is omega I, but it is right due to the so if we take this S in this separate form, it means it means that it is the only it is the derivative of the small s of 1s dy y equal y I of the small s, and this function solves this equation, so it gives the point on the spectral curve, and it means that it is equal to omega I. So there's some tricky simplicity in this demonstration, but there is all the power of canonical transformation behind. And all this means that we have to solve a differential equation in one variable. And if we do so, we construct the canonical transformation from the separated variables to the exponential variables. And it means that we find the solution of all the system. And the only non-trivial problem is this, but this is a differential equation in one variable. Yeah. Okay, let us proceed to the seminar part. Do you remember home tasks?
Compose the algebra, the direction of the positive and negative subalgebra. We can write any x operator as the positive and negative projection of the.
Yeah, very good.
Yeah. And we also know the projection of for any x is going to be this negative or positive part.
Mm-hmm.
So also R over any x is going to be R in general is going to be.
As I remember, it has missed something in the formula. Yeah. Yes. No, I remember some additional term.
Ah, yeah. I can.
Minus or plus R2.
I can. Well, it's okay.
Like this.
Yeah.
No.
So first we compute. First term. This last one.
Mm-hmm. Mm-hmm. Yes, because the projectors. No, it's 0.
It's a 0, yeah.
Uh-huh.
P plus P minus is just acts just like the identity.
Exactly.
Or
Yes, yes, you're right.
This is
Just to commute it, yeah. Mm. Do you remember that this is our R bracket, which is inside the R? So this expression is our R bracket.
It's just.
It's the plus minus minus minus, but doubled.
Yes, two times.
Mm-hmm.
just belongs to plus, and this belongs to
Mm-hmm.
minus. So R over this is over this thing is just 2, and we change the sign.
Yeah, yeah.
Yeah. Now we have to write this plus this. And we can see that this term
Mm-hmm.
is the same one of this one,
Mhm.
but with the sign invert. Also this one is the same
Yeah.
with this one. So this is equal to 2 times Untitled.
X. I think X. It depends on the order. So yeah,
Yeah.
X.
Because these terms are also in. That is it's the same relation that we intend to.
Very good. Thank you. And you see, all part of the construction are important here. So the decomposition, the closedness of subspaces, that they're subalgebras. If not, it doesn't work. So it's quite important condition. And so all conditions of this construction act in what follows. Very good. Do you remember some other problems for today? Yeah, yes, for the Toda Poisson bracket. Yes, very good. They are quite characteristic and important. Who wants to explain?
Maybe I can show, but I don't know what.
We will help you. Please try.
So R1 equals to minus by definition R2 star P12 and R2 equals to R1 minus star P also P12.
Yep.
And I think to find an explicit form, we can let R1 act on Eij product BKL,
Mm-hmm.
which is equal to minus.
What means act? What do you mean by act?
So it's to
Multiplication, just
Yeah,
multiplication.
multiplication. So it's this minus.
So they are from the same space, from the space of tensor square of matrices. Yes, so
Yeah.
we can multiply them.
Yeah, because R2.
R is big R is quite different. Is an endomorphism on matrices. Yeah, a linear operator on the space of matrices.
So this is equals to -1. R2 star is equals to, because it acts on the second, so 1 times R star P12 Eij EKL. This is equals to EKL Eij.
I'm not sure.
Huh?
I'm not sure.
Yeah, because it's P12 it exchange.
No, it acts differently.
Different.
Yes. No. It's not right. This is not right. P over EI over Ej is equal Ej Ei. And if you want this relation, you should write Eij EKL P. Then it is EKL Eij.
Okay, so it should be, so this should be multiply this, multiply P.
Yes.
P1 minus
Yes.
1.
It's involutive, so it's the same. Yeah.
Yes,
Yeah.
yes, yes, yes. And so we multiply this and get minus 1 over 2. R star. R star Eij equals to the sum of EKL. R no, this is the same sum ST. R Ij ST.
Uh-huh.
Right,
Yeah.
so,
Yes. Yes. Yes.
So if also, so we can plug this out and then.
I'm sorry. I'm impression that you do something much more complicated than is needed.
Okay.
So if you just rewrite this P in tensor notations, so
Yeah. So some Ij.
Yeah,
is equal
yeah.
to Ji.
yeah, just Eij Eji, and then apply this to this. That's all. You don't need to consider where it acts.
Okay. Yes. Yes. So R star
Yeah.
is minus 1 tensor product. No. So Eij tensor product R star Eji.
Yep.
So this is equal to sum KL RJI KL EKL.
Mm-hmm. Now the question is to write down the matrix coefficients of the big R and R star.
This big.
Yeah. Yes. What are the coefficients of corresponding to the operator R defined by the decomposition into the sum of two subalgebras?
I'm not very sure about this.
But you understand what to do.
Yeah.
So how to find these coefficients? So you remember that our R was related with the decomposition.
Yes.
And it was related with Gn in B plus
SON.
SON. And
Yes.
so we have to write down the matrix elements of this linear operator.
Yes.
What are they?
We write as the sum of B plus and SON.
Yes. Do you remember that I explained how it acts just on generators?
Yes.
The coefficients here are just the coefficients of this linear operator. Let us reconstruct how it acts, how this operator acts on this basis in the space of matrices.
So R let's say P plus minus P minus Eij. plus is send Eij to B plus if I
Yeah, yes.
greater than j is equals to Eij itself.
If it is better to write just in cases for which choice of indices it is identity.
For I greater than j, p plus Eij sends to the Eij itself, and p
Yeah.
minus sends to Eji.
I'm not sure.
P minus so and so.
Let us write separately for p plus and p minus how they act on generators. So I will write the first row. So pi acts on Eij just identically. Ij if I is less or equal to j.
Yes.
Okay, it means that if this is a generator of B plus, it is preserved by this projection. Okay, how it acts on different, how it acts if I is greater than j. How?
It is equal to 0.
No,
No.
no.
I greater than.
It would be 0 if we consider projection B plus, the decomposition B plus plus and minus. And now we project along different subspace. So we should suppose that the elements of this subspace go to 0. Remember? So minus Eji goes to 0 if I is greater than j.
Yes.
Okay? And then we should extract from this knowledge how P plus acts on Eij.
Is equal to Eji.
Yes. And we know how it acts on Eji. Because if I is greater than j, then j is less than I, so it's the case, the first case.
Yes, so P plus act on this is just equal to
Yes.
I.
So Ej goes to Eji if E is greater than j. Could you write down the matrix coefficients of the operator P plus? It could be represented as a matrix, you see, of bigger size, of n square size.
Yes.
Because it is a linear operator on a space of linear operators. But Eij is a basis in our matrix algebra.
P plus just send Ei to send Eij to itself in both cases.
I will write. So Rij is equal 1 if I is less than j. P plus Ij is just 1 if I is less than j.
Yeah, because it's send Eij
Yes.
to itself, so this is equal
Yes,
to.
but now it's a matrix element of the matrix corresponding to this linear operator. Okay? And now we have to illustrate this. So P plus Ij Ji is equal to 1 if I is bigger than j, is greater than j. Because it acts on this element and it sends it to this element.
Oh, okay.
Okay?
I see. Yes. Yes. Okay, I see.
Please write down the matrix for this matrix,
Okay.
for this operator. I'm sorry. Is it principally clear?
Yes.
Okay.
For P minus, it sends Eij to, because it's SON,
And along B plus.
allow allow this.
Yes.
Allow this P plus.
So all elements of B plus goes to 0.
So 0.
Yeah, absolutely. Yeah.
And then E I J
So now you know that this element goes to itself because it's an identity on elements of this type.
yes, it's P
Yeah.
minus, so E I J I greater than J.
I'm not sure. No. It acts on J minus E J I to itself if I is greater than J. Because it's a projection onto SO. It's an element of SO.
Yes, this is an element of SO.
It is preserved by
okay itself, so it's projection to
but
itself.
To describe the matrix element, we have to define it at action on such a generator. So we should extract the knowledge from this equality. We know that this goes to 0.
Yes. So if this go to 0, then this EIJ must send to EIJ plus EJI. This goes to 0, and I need to send. I'm a little bit confused. Yes, this is go to 0, and we need to preserve this quantity.
Yes.
So it's sent to.
No. So we know that P minus applied to this difference is identity. Okay? But it is a linear operator, and it equals P minus Ij minus
PJI.
yeah, PJI. But this is 0.
PJI is 0.
So it's a definition of this action.
So PEIJ.
Yes.
Okay. So it's sent
To the difference, yes. So it's a projection onto SO, so the image should be SO. So the image of this element is an element of SO. Okay.
Okay.
What is the matrix of this linear operator? What are matrix elements?
So for I smaller than J, P minus Ij equals to 0.
Yeah.
And for I smaller than J, P minus Ij is it Pij minus Pij equals to 1.
No. You see, P minus of Eij is Eij minus Eji for E greater than J. The matrix of this linear operator is such a matrix. Let us write it by small p. Is P Ij KL E KL the sum over KL. It is the P minus of Eij. So we should expand this vector into this basis. Okay? And these coefficients are the matrix coefficients.
Not quite sure.
So let A be a linear operator from Rn to Rn.
Yes.
What is the matrix of this linear operator? We should take A acting on the basis
Yes.
vector I it will be some A, I, J, A, I, J, I, J, E, J. So we should expand the image of this vector into the basis. And the coefficient will be the matrix coefficients. So
Okay.
now the image of this vector is the linear combination of vectors. So there are two non-trivial coefficients in this matrix. In the column of this matrix. Which one? Which ones?
We have two non-trivial coefficients of this.
Yes.
And then
I will so P minus EI is 1 if IJ is greater, I is greater than J. It corresponds to this part.
yes.
But there is another one in the same column.
So P minus IJ JI
Uh-huh.
is equal to, let's say,
Minus 1.
Minus 1.
Minus 1. Greater than J.
Greater than J.
Yes, perfect. We have to accomplish. Now we have to write down the matrix for the difference of projectors.
Yes. So
It will be the matrix.
They're just the basis of B plus F.
Sorry?
They're just the basis of
Yes, of course. But let us write it explicitly in terms of matrix coefficients.
P minus. So when I smaller than J, R equals to P plus minus P minus equals to
Mm-hmm.
1. So I greater than J.
Yes.
And
No, but one is the matrix coefficient. IJ, IJ.
yes.
Uh-huh. Okay. I prefer to write
Here,
R, IJ,
Oh, yes.
IJ is equal to 1.
okay. Yes. Okay. And for I greater than J,
Yes, it's a little bit more complicated.
equals to P plus equals to P plus minus P. So P now P plus IJ JI equals to 1. And this is 2 minus 1. It's equal to minus 1. How do we change this IJ to that?
No. We will not, but we will later calculate the other coefficients. So, first of all, you should calculate this for I greater than J. And then we will calculate the element, this element.
Okay.
These are different elements of the matrix.
I see. IJ, yes. So this is 1 and this is minus 1. So it equals to 2 I greater than J.
Yep.
And another case Ji equals to
I'm sorry. Why IJ? No. Why it is minus 1?
Because we have this relation.
Mm-hmm.
So it is minus 1, minus 1, minus 1.
P minus for I. No, it's 1. P minus ij ji is equal minus 1 for I greater than j.
So it's this ji.
Uh-huh.
Ji equals to
Yes.
minus 1.
And this coefficient means that Pij is equal 1, also for I greater than j. P minus.
Yes,
we are quite close to the finish, but
yes. So 1, so this is 0, and then for I, and we have P plus ij ji minus P minus ij is equal to, this is equal to 1 minus,
I don't agree. It is not 1. No. No. No, it is 0. P plus. So it is 1 if.
so I smaller than 2.
Yes. And it is 1 if I. But with exchanged indices here.
Yes, so.
No, this is 0. So it is minus 1.
Minus j, this is 1,
Mm-hmm.
and this is minus 1.
Okay.
So this is 2.
Yeah.
So.
Yes, that's right.
also
Yes, right. Yes, that's right. Okay, very good. We have now. Okay, please. The next step is to calculate the R star, the conjugated operator, and its application to the transposition matrix. So this is the good answer for R, for the matrix R. Now we have to apply this R to P. You remember that R1 is minus 1, 2, R star 2 applied to P.
1, 2, yes.
Yes. How to apply it?
Okay, so R2 star, R2.
Sorry, Al. What are we doing now is for open Toda or full Toda?
For full symmetric Toda. It fits also for the open Toda, but it degenerates. So it is a general description of the Poisson structure for the full symmetric Toda system. It reduces to the open Toda chain, but it can be simplified for the open Toda chain.
So R star.
No, I suppose we have to transpose this matrix. No, you're right, KL. Yes, you're right. Very good.
Okay. So R, J, I, K, L, we, so we apply
Mhm.
different conditions.
Yeah.
So fix j equals to k, I equals to L, it's for I smaller than j. And this is equals to E j I
Mm-hmm.
for I greater than j. J.
R. Uh-huh.
This is
To J. To if. Is it right?
yes.
Uh-huh.
So for I greater than j, we have this minus ei because we fix k and j here, so it's minus 1.
Mm-hmm. Mm-hmm.
And I greater than j, this is 2 ij I j.
Mm-hmm.
So we find this R
Yeah.
R star
Yeah, yeah,
j
yeah.
I.
Yeah, yeah.
This is equal
Yes, yes, I suppose you are right, yeah.
to
Mm-hmm.
yes, and
Mm-hmm.
right.
Mm-hmm. Yes, and you have written the application of R2 to P. P1.
Yes,
Uh-huh.
P1.
Yes.
Yes, yes.
Yes, I obtained something very similar, very close to this. I suppose this is correct. Yeah. Okay.
So we find it. We find the explicit form for R1.
Yes, yes, that's right. R2 is very close, and it will be different from this by the signs of the symmetric and skew-symmetric parts. I suppose they will have the same part of this expression and this expression, and the diagonal part here, J, and this part, which is also symmetric, you see, this part will be with the sign minus in R2, and there is some general meaning of this fact. But principally, you done correctly this calculation. Thank you very much. Please take the place. Okay. Do you remember some other interesting problems from the previous class? there was some discussion about the characteristic polynomial and traces of powers, but I think that we finished it last Monday. Okay. If not, I will tell you.
You mean like the Poisson bracket of the traces of the powers of the
Yeah. Yes. We discussed this, and then there were some consideration of characteristic polynomial of the Lux operator. Why the coefficients of the characteristic polynomial represent another basis in the space of integrals.
Yeah.
Yes, but it's quite general, and I would like to tell you a little bit about the generalization of the separated variables obtained for the SL2 Gaudin model. It is called the Stachel systems, and it is also a quite general approach in integrable system. Stachel systems. So it deals with, this approach deals with such a situation. Let us consider a polynomial on two variables, which is the sum of coefficients. I would name the object by the correct names, I, x, y, plus h0, I from 1 to n. And now we consider the phase space R to n of variables xi, yi with the canonical with the canonical Poisson bracket. It means that xy, xi, yj is delta ij, and all other brackets are trivial. So we will think about this equation also as equation of an algebraic curve on R2. xy are some coordinates of the point in R2, and in this we consider an equation r x y is equal 0 is an algebraic curve in R2, but it is always useful to consider a complex extension. And now we would like to consider h as parameters. So to consider the space of polynomials of such types. Okay, so it's some family of algebraic curves in R2, depending on values of parameters. If you like, you can think about these parameters as the values of Hamiltonians. But different values of Hamiltonians choose different algebraic curves on R2. Now let us find a curve of such type passing through endpoints. P1, Pn, and R2, given by the coordinates xi, yi. So it means that we have to solve this set of equations. So for all I, have the sum over j, hj, rj of xi, yi plus h0 equal 1. And so we have n equations for I need maybe to fix. So h0 is fixed as a constant. Fixed constant. And equations for n parameters h, j. So it means that a, j are functions on R to n. Remember, we have R to n with such pairs of variables with the canonical Poisson bracket. And if we have yes, we have here R0 of x. Yes, that's better. That's much better. I'm sorry. Yes, now we have n equations for n variables without any necessary additional choices. So, and if we solve such a system, we define h, hj as functions on our space R to n. Lemma h I are an involution. So whatever polynomials you have chosen here, if hi specializes a spectral curve such that the endpoints lie in such a curve, this choice of values of Hamiltonians define a commutative family, Poisson commutative family. And this is quite general setup. So quite often known integrable systems can be interpreted in such a way. So that's why we make a small remark on this consideration. Let us try to demonstrate this lemma. The simplest way is n equal to, just to choose generic polynomials on two variables. So you see, all depends on the choice. For n equal to, we need the choice of free polynomials. Free polynomials describe the dependence of Hamiltonians on points on the spectral curve, on n points on the spectral curve. For you, this set of n points is a divisor, defining a linear bundle on the spectral curve, and this linear bundle has a representative on the Jacobian, which is the g-dimensional torus. Not for you, but for all who are interested in algebraic geometry.
But problem is if we use R, if you use a not algebraic closed file.
Yes, it's quite general. You can consider more general context. Okay, let us demonstrate this lemma for n equal to for generic choice of functions R. It is not specific for polynomial functions. It is quite general. Do you need some comments? You look hopeless.
I mean, I didn't get the question yet, so
Do you understand the definition of functions, of how we define functions h as functions on R to n?
So the HR are just like arbitrarily functions.
No. They are quite. They are absolutely definite. So, just one time. So we consider the set of the linear space of equation of such type. Okay, it is the n-dimensional affine space in the space of equations of curves on two variables. It depends on parameter hi. So in this part, hi are just auxiliary parameter. Then we choose n points in R2. N points in R2, it's the point of R to n. Okay? We consider the natural Poisson bracket on this R to n, or by another way, on the set of n points in R2. My statement is that if you choose n points, then there is only one curve, spectral curve of this family, which pass from these n points. It's a general setup from linear systems. Is it clear, or please say? It's not difficult to comment. I thought that it is well understood.
I don't know, maybe, I don't know if it's okay, but maybe a general idea from the equation of the spectral curve. You have a development which is the lambda square plus the determinant, which is the lambda square plus the sum of hi plus hi square. And then you can use the trace of Lk and use this development of powers of c minus ci. So maybe an idea could be trying to express hi and ha as traces of L.
No, it's very general.
It's more
Yes, more general. This is much more general. Whatever polynomials you choose, you get a commutative family. But how we define functions h on this space R to n, we impose the condition that the curve from this family pass through n points in R2. It defines uniquely the curve. Is it clear? So we have n equations. So here the points is fixed, the polynomials r are fixed, the only parameter h are free. But it is the linear system on h, the system of n linear equation on n parameters h. So h is defined uniquely, and that means that h are functions on this set of n points in R2. If we fixed n points, there is only one curve from our family which pass through these points. Because of the system of linear equations. Is it better or not sufficiently?
Now I get the question. So, but I'm wondering that the starting point of this question can be starts from picking up two the curves which satisfy the equation.
Yes. N equal 2.
Yeah, exactly.
It means that it means that there are only two Hamiltonians. You see, it means that Rxy is h1 multiplied by some polynomial plus h2 multiplied by another polynomial plus r0 xy. And now we have 2 points, x1, 1, y1 and x2, y2. And they ask that such an equation is satisfied. We ask r x1 y1 is 0 and r x2 y2 is 0. And this allows to absolutely uniquely define h1 and h2. Okay? And it means that h1 and h2 are functions on this space. The statement which we have to verify that if the Poisson bracket on these variables is canonical, then these functions are in evolution. So let us try to do it quite directly. So to solve this system of linear equation and to calculate the Poisson bracket. You will see the phenomenon and then we will try to generalize it. Have you succeed?
What do you mean by direct? Just do the partial derivatives.
Sorry?
What do you mean by direct?
By? Direct?
By partial derivatives?
No, by partial derivative. A partial derivative to calculate the Poisson bracket? Yes, yes, we have to calculate as functions on the phase space. But with the canonical Poisson bracket.
So x1, y1, x2, y2 are the roots of the
Yeah.
equation.
Yeah.
Yeah, I think I.
So they are points of the
Yes.
spectral curve.
So the R's are like the Poisson bracket we had before for A, Yj, I think. No, those were like coefficients from the equation. So maybe. Yeah.
So here R are polynomials with constant coefficients. See, they're fixed. Ri are polynomial with constant coefficients.
N is n in m, doesn't change the result, right?
Sorry? N?
Yes.
That's true for auxiliary n, for all n. But it's maybe better to start with a simple case when you can write all the... So you see, you have just two linear equations and you have to write down the explicit formula for the answer. Is it clear? Or? You have it?
No, but we should try to express one of like H2 in terms of H1.
No, H1 and H2 in terms of these variables.
Okay.
How to say?
You could just say air in x1, y1,
Yeah.
and air in x2, y2, and then do the Poisson bracket of it.
Yeah.
And then you will obtain the cross Poisson brackets, and you will remain only those.
Yes, something like this. So I'd like to... You see, we have to solve such an equation. H1, R1, x1, y1, plus H2, R2, x1, y1, plus R0, x1, y1, and H1, R1, x2, y2, plus H2, R2, x2, y2, plus R0, x2, y2. But now it's a linear system on H1 and H2. And for general choice of polynomial, it gives the unique solution. And it means that we define functions H1 and H2 on our space R4, the space of points x1, 1, x2, y2. And this is the Poisson manifold. with very canonical plus one bracket. You see, if we define H1 and H2 from this system of the equation, they will plus one commute. Do you know the classical theorem about quadrics and 5 points on the plane? That there is, for general choice of 5 points, there is only one curve of second order which passes through 5 points.
Second?
Second order, yeah. If you consider just the polynomial of second order, but a generic polynomial of second order, and choose 5 points in generic position. There is some subtlety in defining the generic position. Then there is only one one curve which passes through 5 points. So it's a very beautiful theorem from analytic geometry, but it deals with the same concept. So there is a linear family of polynomial equations. So a generic polynomial has the form plus. So it is written in such a specific form: 2y2 plus x y0. So there are generic coefficients here, and if we impose 5 conditions passing through 5 points, these conditions define the coefficients, 6 coefficients, up to multiplication by a common constant, by common constant. Okay, so it is also a linear system of 5 equations on 6 variables. And for generic choice of points, it defines uniquely the curve. Now we also have a linear family of curves defined by polynomial equations, and dimensional family of curves. And they impose that our curve passes through n points. It allows to define explicitly the representative of this in this family of curves. And our curves are characterized by the values of coefficients which we identified with Hamiltonians of some dynamical system. So all this approach says that if we do such a calculation, the coefficients which are defined by points are commutative Hamiltonians. So let us calculate it explicitly. So we can find the solution of this system just by the Kramer's rule, by the ratio of some determinants, or as you like. And please try to demonstrate this. But I suppose it will be your home task. So home task 1 and home task 2 will be about the SL2 Gaudin model. So this is true for all generic choice of polynomials Ri, and home task 2 will be to calculate explicitly the coefficients to calculate explicitly coefficients of the characteristic polynomial of that L of z minus lambda e. There L of z is our f z b of z, c of z minus e of z. So it's characteristic polynomial, as I have written, is something like this. It is lambda square plus sums hi z minus zi square plus I will write it as hgbf fi z minus zi. Yes, 1 to n, 1 to n, and there are no other terms. My statement is that there are no other terms. It is because the determinant of L goes to 0 at infinity. Yes?
So here hi and fi are bases.
Our theorem says that all coefficients commute. Okay? So the question is to calculate explicitly, yes, to calculate hi and fi, and to find Casimir functions. Okay. So we finish for today. Good continuation.
Here